Hello, and so today is our first video on the nature of light in this segment for the grade 10 top students. And again, this is not definitive. Textbooks have been written on these topics. The idea is to give these grade 10 students introductions to some of these ideas. I'm going to be talking at different times about ideas that are more advanced, but there will not be the substantive mathematics that goes with it, but simply to make you aware of where some of this goes and where some of these amazing people have made other contributions that were used in other places and situations. So today we'll talk first about the initial musings of wave theory with light with Huygens, and then Newton's work, and then a big gap, and then the interesting work at the beginning of the 1800s, primarily by Young and Fresnel, Poisson, and Arago, and the others. And so hopefully you'll find this an interesting and enjoyable exercise. Again, remember that the main obligation you will have to me in this course is simply to explain these ideas. It's not going to be problem sets and things like that. That's not where we are at this level. So I hope you enjoy it. Thank you for watching. So the first person we meet in our study of the nature of light is a Dutch scientist. His name was Christiaan Huygens, who was a very capable youngster. His father was friendly and supportive, and was friends with Galileo and Descartes, and these people clearly influenced the young man. His sum total of his work is truly remarkable, contributions all over the place: astronomy, physics, time management, light, music, and so on. He even taught some math to Leibniz, but interestingly enough, he wasn't willing to accept Leibniz's teachings on calculus. Derived centripetal force concept and solved the equation for the period of pendulum. But the point relative to our story is, of course, his thinking of the point source and how it leads to the development of light phenomena and light as a wave. And as we stand here today, his ideas have great import, but in those days they weren't accepted quite the same because of the shadow of the great Sir Isaac Newton. And so they kind of had to sit around a little bit. And what you're going to see in this whole story is there's been a smattering of ideas all over the place here and there as the imperfect work of science happens and slowly coalesces into what is established to be a reputable fact. So what I did a number of years ago is I created an animation here to show you how Huygens' principle works. Now this is slowed down a bit, but imagine dropping a stone in a pond and how the ripples of the water radiate outward. So the fact that it goes faster or slower is not as important, but this is a two-dimensional equation that does this, and it's actually the equation you see here that is animated. This is a 10-frame animation, so there's 10 calculations, 10 pictures, and then it's just shown in sequence. Now, the reason I'm showing you this is that I wanted to convince you that Huygens' principle, at least in mathematically, actually works. Now, without the algebra capability of these machines, it is a pretty daunting calculation. But I just wanted to show you. So this is the beginning of that anyway. So in case you wonder what I do in the summertime, this is an example of it a number of years ago. So what I did was I took that initial Huygens point source equation, and then I positioned 100 of them right beside each other. And then I had the computer run these 100 at the same time, where each of these spots, these single point sources, would interfere with each other. Now, if we take, for example, in our bathtub, if we take a piece of wood and we go up and down, we're going to get straight waves marching across, as you would expect. Huygens suggested that these are simply the interference pattern of a whole bunch of point sources. So this animation you see here in the computer screen is exactly that. This is the animated effect of 100 of the point source equations I showed you a minute ago, all side by side, and animated with respect to time. So these, if you will, the sources are in the center. The board is going up and down in the center. I've angled this slightly just so you can see its action. It's a little bit more coarse than the original animation, just so for processing time. So I thought this was pretty impressive to show the work of Huygens, and how well it comes out to pass and explain some of our phenomena. But we're not done yet either. So what I've also done is to show you how Huygens' principle can simulate diffraction. So once again, I take my series of straight waves, and what I do now in this location here is I introduce an obstacle and I begin to narrow it. So there, now that's the broadest case, and as it slowly comes together here, you can see that the effect and the V shape, if you will, of the mechanical waves, there they are, straight waves, slowly coming together now, okay, as the effect of the Huygens point source allows it to leak around the corner where it really shouldn't be going. This is a double slit, or single slit, pardon me, where there's obstruction on both sides, but either way, it's the same concept. So the next player in our game, of course, is the first of the three great men of physics, Sir Isaac Newton. Now, Newton's story will be told to the grade 11 course, so if you're interested in his details, you can go over there and have a look. But from our standpoint, he's the first person who really does a scientific investigation of light in a true scientific way, and he published his work in his book called Optics in 1702. He saw the spectrum of the sun. He was able to find that you couldn't subdivide a spectrum yet again. So, for example, if you had a spectrum and you put yet another prism there, you wouldn't get yet another spectrum. You would get simply a finer version of the first spectrum. He showed with a lens and a prism that you could recombine the spectrum back into white light, and so on. And these were all very important ideas, but Newton wasn't an acceptor of the wave theory because he felt that diffraction would lead to light going everywhere and you would never have any shadows, among other things. Now, with all of that, he deduced that light somehow was particular in nature, but his reasoning vis-a-vis quantum mechanics is flawed, and so we really want to be careful sitting here thinking that he predicted, quantum mechanical phenomena at 200 years ahead of time. But anyhow, Newton, so in this particular instance, Newton, in some respects, holds things back a little bit because we'll see in the early 1800s that there's a great resurgence in the concept of wave theory of light. And Newton was certainly, in many ways, a particulate guy, and his reputation held back that work a little bit. So here's a slide showing some of Newton's developments. The primary one, of course, is Newton's rings, which, of course, is a straight diffractive effect or interference effect of light. So there's wave theory right in front of you there, but at the same time he felt that telescopes would always be affected by the chromatic aberration. In other words, that the prism separates the colors, as you can see here. So he built a reflecting telescope rather to show that you could build a telescope without those problems. Now this chromatic aberration was fixable later on, as you can see in this diagram here, but it was fixed later on using other lenses, but at the time that was considered an insurmountable problem, which is why we went with the mirror telescope. But of course today we use mirror telescopes all the time because you can make a really big mirror where it's pretty difficult to make a really big lens. So as I said before, Newton's reputation carried the day, and so not too much happened for almost 100 years. As the century turned into the 1800s, a gentleman scientist named Thomas Young performed an experiment which started the wave theory of light moving. Now, he was one of those gentlemen scientists at the time, classical education, spoke 3 languages, was acquainted with 11 more, which is often in those days the typical way they were educated. And he was one of the translators of the Rosetta Stone. I would say a minor contributor, but nevertheless still. And of course, here's a picture of the Rosetta Stone, and the idea being that it was much bigger than that at the time. But what you had was ancient Greek, Hebrew, and hieroglyphs all on the same tablet. And this allowed for the initial translation of the hieroglyphs, which before were for the most part a lost language. And so this is really the beginning of Egyptology as we know it today. For those of you who watch television, just as an aside, if you've seen the show Downton Abbey, the castle that they're in, Highclere House, was the home of the Lords of Carnarvon. And the seventh Lord of Carnarvon was one of the prime discoverers of the tomb of Tutankhamun, so way back in 1922. So just a side little story there. Now, if we take, sometimes I think that Young's work is misrepresented in the schools. You see here a diffraction pattern interference pattern, caused by two sources, 2 point sources, simply just putting, if you will, 2 rocks in the pond, keep doing that, and you get an interference pattern as the ripples move outward. And that's perfectly fine. If we put a screen somewhere and look at the resulting light pattern, we get this perfectly bright lines, perfectly spaced, and the equation for all of this is simply the cosine squared. So you're going to get these peaks, and they're perfectly spaced, and this can be used in other aspects of optics. But the problem is that Thomas Young used diffraction to do this, and the problem with that is that the holes of the diffraction panel are not point sources. They are hundreds of times the width of a single wavelength of light. And so when you look at a diffraction pattern that is done by a double slit experiment by whomever, what you find is not that ideal pattern you saw a minute ago. In fact, you see this pattern instead, which is the double pattern, which is in the purple, with a single slit pattern superimposed over top of it, because the single slit interference pattern is occurring because the slits are sufficiently wide. So you're getting both effects at the same time. And this is something that isn't properly explained, I don't think, in most books. And this is when I went to high school too. We did the 2 point source experiment as a way to justify the work of Young, which is really not true. So we see here a double slit diffraction pattern. And so the little dots that you see as we go across, those are the peaks of the ideal 2-source pattern, the cosine squared function, if you will. The reason that the intensity comes and goes and modulates is because the intensity of the 2-slit pattern is being multiplied by the intensity of the 1-slit pattern. And this is because the slits are significantly wider than a single point source. And we get this combination, if you will, of both patterns. Now, this is certainly a wave effect, no question about it. And in that respect, Young's work is sound. But we have to be very careful if we want to use Young's work as saying that this 2-slit pattern treats them too as 2 point sources, because it does not. So the next player is a unique individual, as they all were, I guess. He didn't live a great length of time because tuberculosis was an illness he had all his life, which made life for him, I'm sure, quite difficult. But I think he was as smart as Huygens in the sense of his general ability. So he was the son of an architect, and depending on who you talk to, he couldn't read until he was 8 years old, but whatever. But he progressed rapidly and entered the École Polytechnique at only 16 and a half and did very well in many ways, initially as a companion to his brother, but I suspect in the end he picked up on his own. He finally finished up as a civil engineer, primarily of bridges, and originally he was asked to work on some things in the south of France, but later returned to Paris and worked on ones in the city, and part I suspect probably because of his illness. Fresnel showed up in prominence. He was already doing a lot of science, but he showed up in prominence when there was an essay competition held in the 18 teens, a little bit after Napoleon was finally out of the picture. And it was to explain the work of Young, primarily with the idea of using Newton's corpuscular theory. There were 6 people on the committee. 4 of them were staunch particle type approach, and then there was a couple who were thinking of the wave approach. Regardless, Fresnel wrote his paper based on his idea of the wave model, and it is a tour de force. This is a very complicated paper with a great deal of mathematics in it, and ultimately they really didn't have very many papers to judge from. He was given the award. The other paper was considered flawed, but nevertheless there was a great dispute about whether this was proper. And if we look at the next player in our little story here, Simeon Poisson, who was involved with this. Poisson, of course, was no aristocrat. He was raised, in fact, to have a healthy disregard of them. This was not about prejudice due to class, which is not uncommon in those days in Europe, but this was actually more of a prejudice based on the sense of what he thought was correct. And he was not in favor of this wave foolishness to go against the great Newton. But Poisson was a brilliant mathematician, and so after Fresnel's papers were taken in, he could read the math, and he decided to craft a way using Fresnel's work that would show that Fresnel's work was incorrect. And thus he invented and solved a problem where, for what we call the Fresnel or Poisson or Arago bright spot, Fresnel was confronted with this work. Fresnel agreed that this was done correctly and that this should exist, and this astounded Poisson. And so within a week or so, as the references suggest, Arago went out and did the experiment. And you see the story of that as we go ahead here. Now, in addition, and I thought I'd spend a bit of time just sharing you a little bit of the work of Auguste Fresnel, because he's a pretty sharp guy and made a lot of contributions that make quite a difference even today in our society. Now, this slide I took from Thomas Eisinger, who's doing master's thesis on this topic. And this is just a generated diagram, of course, but what you have here is you have a light source, you have a disk, and you have a screen. And so the black is the shadow of this on the screen. And if you set up everything correctly, this is probably 2 or 3 millimeters in diameter. This might be a meter away or whatever it is. You're going to get, if you do it right, you'll get that spot right there. And like I said, I've talked about it being the Poisson spot or the Fresnel spot or the Arago spot. So Fresnel's theory is what predicts this. Poisson's the one who implied the theory, perhaps trying to discredit Fresnel, but it was the one who predicted it in the sense of using Fresnel's theory to do so. And Arago's the one who performed the experiment that actually showed it happening. So you pick your favorite person. I tend to lean towards Fresnel because he came up, this is a pretty demanding theory, and he did it pretty much on his own. So this is another one from Eisinger, and what you're getting here is a simulation, not an exact experiment, but it does show what happens here. So this is looking, if you will, looking on the back side of the disk, looking backwards towards the light source. That would be at a right distance, perhaps a meter or so. This is a 2-meter disk, maybe a meter from the source, and then, I'm sorry, you're much closer to the disk here, and you can see the bright spot very clearly in the center. And so this was, prima facie evidence that the wave theory of light had tremendous support because of this, what was perceived to be a very challenging prediction, because this seemed to be completely counterintuitive to what you would expect. Now, this is a diagram taken from some simulation work done at MIT, and what you see here is, of course, the disk, and the light coming from over here, okay, coming this way. And then you see behind the disk, these are all diffracted light here, and you see the bright spot forming, okay? So if you put a screen here and view this, anywhere in this area, you will have this dot. If you just draw a slice through this anywhere you want to, you will get the bright spot effect. So let's have a little look here at a diffraction situation and what we could perhaps understand about it. Now, the work of Fresnel is very complicated and uses advanced forms of calculus, so we're certainly not going to be doing that in grade 10. But we maybe can do a few things here to understand it a little bit. So as a ray comes from the edge, right at the edge, ignoring this rest of it here, of a obstruction, okay? the ray will go to the screen, which is where we will envision the pattern. And you will have rays that will come straight, okay? Ones that will take a slightly longer path, and a slightly longer path again, and so forth. And this will change their phasing, the time it takes for them to get there. And so what we want to think about is, what does that do? So if we take, for example, n equals 2, so we have lambda over n here, 2 lambda over n for the blue one, and 3 lambda over n for the green one. And again, these would be much closer together in the real world, but that's just for display purposes. So if we choose 2, then these are all out of phase. So this is an integer multiple of wavelengths. This is then half a wavelength out of phase, a full wavelength, so these two agree, and then this is a half. So what you'd end up with is every other wave being exactly 180 degrees out of phase. And they would cancel out, and you get nothing. Now, if we take instead a much finer situation, say 18, then we would have only 20 degrees angle here. And so the change now is more progressive. And what's more interesting is, because the further out you go, okay, the further out we go, the closer these are together to create a different angle. So to put it another way, let's look at it this way. We have these distances here. Okay. Now if you want to maintain the hypotenuse distance, these will get smaller over time. And so you'll end up with a smaller ratio just because of the geometry of the distance factors. So these directions of how much they get out of phase will change less and less. And obviously in real world, this n then is basically infinity, okay? It's a very large number, and we're dealing with incredibly close waves, okay? All right, so let's see what that looks like in our next diagram here. So if we were to graph these, so the light wave, we'll just take it in pieces. So 20 per degrees, however long that would take, would be a certain point. Then we'll turn the arrow, turn the arrow, turn the arrow, and keep on going, okay? And if we do this enough, you get this effect. So the true ray might be going over to here, okay? So let's be very clear about this, is that this wavelength is going to be going many, many times. And you get this effect because as it increases in distance, okay, the curvature will tighten, all right, because the effect is different. As I showed you before, those distances changing as you go further up. And so what this does is gives us this spiral, which is internalized and tends off. And this is known as a Cornu spiral. Now in the next slide I'll show you a computer-generated version of it, which gives you a very good, and then a three-dimensional version of it, because we can also see this going into the board. Now we can use different mathematical modeling, but in this example we could use time. So as this thing progresses, it also goes downward, okay? And so you get a three-dimensional spiral effect. And so once again, what are these things? They're representations of how the light is traveling. What phase is the light traveling? Okay, so if it just goes straight through, if it's, so let's just draw another way to look at this. So if we have, here is one wave, okay, and if it's 180 degrees out of phase, it would look, the other wave would look like this one, and you get nothing. But on the other hand, we can have situations where the phase shift is much, much less, like this is. Okay? And so the difference, if this is this is theta here, okay, and this is 360 and 0, then this phase shift might say be 20 degrees. Okay? So then where this starts, this effect here would be the first one there, and so on. And so you get imagine Also, the light, imagine the light as it travels this way as simply an object that's spinning, okay, and the arrow points in the direction of where it happens to be. And its rate of spinning is the frequency of the color of the light, the frequency of its emission. So as it spins, okay, and the light's still traveling however long it takes to get to the barricade, okay, you can get this effect that we notice graphically more than in practical cases. Okay, so I just did a few calculations just to give you an example of how this can happen. And again, this is an algebraic concept more than a real life. The light isn't traveling in a circle. The light's going in straight lines. There's a representation of how the light is changing its phase shift. So if the frequency of red light is 4.7 times 10 to the 14 hertz, 10 to the 14 cycles per second, the distance from the obstacle to the screen is 1 meter. The speed of light is 3 times 10 to the 8 meters per second. Then we take the time it's going to take for the light to travel from here to here. It's going to be 3.3 nanoseconds, 3.3 billionths of a second. But in that 3.3 billionths of a second, we multiply that by the frequency, we're going to get 1.5 million oscillations, if you will, cycles, so to speak, if you will, before we get to here. And so if you can imagine this little arrow spinning like a top, that in the time on a little boat as it spins to get to here, okay, this is spinning as it gets to here. This will spin roughly 1.5 million times before it gets here. So what I'm suggesting is that we look at, as we break this up, we can get this effect of how these things are rotating, okay, and just position them as they come. And you can get this mathematical construct, which we call a Cornu spiral. Now again, there's no fancy mathematics here, but what I like to do when I introduce these things to you folks is to give you an idea of some of the fun things that are coming your way in a few years. So if we, as you saw in the last slide, I showed you Cornu's spiral. Now that was with a straight edge, so you only have one side creating the diffraction pattern. Of course, if we have a slit, we're going to have one on either side, creating the wavefront effect on both sides. So this is and this is of course an ideal thing that can show up, and this shows it pretty well. But it's a remarkable thing that shows up in so many other aspects, as I said in the previous slide. We see here the Cornu spiral diagram. It is kind of interesting to show this because when you go off of a highway exit ramp, the cars are moving very quickly and the curve cannot be very aggressive. But as the cars slow down and you can move onto the next roadway, the curve becomes tighter. And they generally follow this path, very similar, at least in part, of a Cornu spiral. So it's just kind of interesting, something completely removed from light. If one of your grandparents was an architect or draftsperson back in the 60s and 70s, they would have with them a plastic device that allowed them to draw different curved shapes. And this was known as a French curve. And it also, I believe, had Cornu spiral characteristics to it, hence the name. So it's just kind of interesting how all of these ideas that start with light are moving around and ultimately come to affect our day-to-day circumstances as well. Now here's we saw the wavefront spiral. And if we were to let that extend in this example, we can use different ways, but we could just look at it over time. Where, you know, this is the first one, and as time goes by, we stretch it out, okay? This creates a spiral, and because the distances are further and further, the diameter gets slightly smaller every time, because as you move away, it doesn't take as much to create a half a lambda or whatever fraction of a wavelength difference. And this spiral, seen in 3D now, is the Cornu spiral over time, or over this example here. And now what we'll do is we look at projections. It's now in 3D. We look at projections in the XY, YZ, and XZ and see what that tells us. So this video takes that a Cornu spiral that's been stretched out over time. And we project it in the 3 planes. This is typically XZ, XY, and XY on the flat, YZ, and XZ. And you see these 2 patterns here. When you combine these 2 with a bit of calculus, you get the diffraction pattern that Fresnel observes with a straight edge. If you look at it long ways, you obtain that Cornu spiral that we've actually, this is how we got this. And so it's just neat from a non-mathematical point here to show you how you get into some very interesting things by looking at the math a little differently. So just to make sure we understand what these diffraction patterns are showing us, we have a sharp edge, so a razor blade or something quite nicely machined. And let's imagine it's situated so that it's along the y-axis. And you stand back from that and the light is behind the razor blade or whatever, then the razor blade would be right at the point where the y-axis would be right at the point where the razor blade covers up the light. On the right-hand side of the y-axis, it should be darkness. We shouldn't see anything. But as you can see, the intensity curve, okay, so we have the distance from the occultation here one way or the other, and then the y-axis is the amplitude, how bright we see things at a particular distance. So on the right side of the y-axis in this graph, you are seeing the intensity that is viewed while you're completely covered from by the obstacle from the source of light. On the left-hand side, you're seeing the brightness of light you're seeing just as the light comes into view. And this interference you see, this 137% peak and beyond, is caused by the, well, it can be modeled at least, by the Huygens patterns right beside the obstacle. So here's another graphic to try and convince you of this. So if we look at, for example, the upper 2 diagrams, we have a flashlight and we have an obstacle, and we shine a light. We expect, under normal conditions, that the shadow will be geometric. It'll go straight across, and behind the obstacle will be completely dark, and out in the area where the light is visible, we will see the light. But instead, we don't get that. What we get instead is this diffraction pattern, where some of the light sneaks around the corner, and then the intensity of the light in the area where it should be completely lit up is modulated because of the interference. And this is all predicted, like I said, from my work earlier here in this video. So there's 2 different ways to hopefully get that you understand what we're trying to do here. So these straight edge diffraction patterns that come up are sensitive to the wavelength or energy wavelength of light as it's perceived. And so you can see how they get out of phase very quickly. And if you think red light is, say, around 610, 20, 30 nanometers, and blue light, say, 400 nanometers, I mean, it's not hard to get out of phase pretty quickly. And so this would, of course, when you add these together, it's going to tend to smooth the pattern, as you'll see in the next slide. When you look at these type of diffraction patterns, as I show in other slides, the pattern is sensitive to color. So if we take like a laser and get a very precise pattern for a particular wavelength, but if you have a bandpass where, let's suppose, your detector is looking at light over, say, 100 nanometers of bandpass, so say from 500 to 600 nanometers or something like that, then these waves will all superimpose, and this tends to dampen the pattern. So you'll see that there's still a very dramatic peak, and the second peak perhaps, but then it starts to die off pretty quickly. And often this is the type of measurement we have to make because our equipment can't observe the natural phenomena in a discrete wavelength because there just isn't enough light available to us. Now here's a graphic example of a Fresnel lens. So if we were looking at the example that Fresnel used later on in his work to to make lighthouses with a given amount of illumination shine further away, you have to take more of the rays and focus them in a beam. Now, how do you do that? Well, as you'll see in the second half of this unit when we do geometric optics, but just to show you some of his work very simply, we could take half of what we call a biconvex lens, or sorry, just a planar convex lens. So one side's flat and one side is a curve. And as the light comes through this, okay, and it's, remember that the light source is a point here somewhere. So it's coming out and it's going to get bent kind of, sort of, into a beam. And the point, though, with this is that the lighthouses are really big. This could be 2 or 3 meters, which is a pretty big chunk of glass. And this distance here could be, a foot or more. And most of the light is going through the center part. So when that happens, you absorb a lot of light, and the effect that you're trying to achieve is lost. So what Fresnel did was to preserve the curve at the outside and get rid of the thickness in the middle. So you can see that we have chunks of the curve on the outside, but with nothing else there. So the lens itself is now very thin in comparison, and it looks distorted. Now, if you try to look at an image through this, it's going to have some distortion, won't be very pleasurable, perhaps. But that doesn't matter, because with a lighthouse beam, we're not worrying about that particularly. And so as a consequence, these Fresnel lenses allow then, if you look directly at them, make the light a lot brighter. Now this, of course, works for boats at sea, but when they worked them, you had 2 choices. You can have a lighthouse with a single source, which was often the case in the old days, and then you had the glass thing rotating around that with, say, 4 or 2 or whatever Fresnel lenses. So if you were at sea, when the Fresnel lens was lined up with you, you would see a flash, and then it would go away, and then you'd get another one. And this gives you a sense of where it is, because you're getting the light concentrated and shining in a direction that is, reasonable above the ocean. It saved a lot of lives, because between one lighthouse and the other and the other and the other, they could take sightings on them. Knowing the distances that those lighthouses represented, they could tell exactly where they were at sea and hopefully be able to find themselves in less than ideal conditions. This also works for railroads. With cars, we can stop a car in roughly 100 meters, so the lights, although they can be shielded a little bit and so on, the problem isn't quite as great. But a train takes, a mile, 2 kilometers perhaps to stop it if it's moving quickly or quite heavy. And so the problem there is that our train operators have to be warned in advance, well in advance, of the signal situation. Now, clearly today we have electronics and so forth and automatic train control, but well before today, this was the challenge that the engineers had. And so if you put Fresnel lenses in your train signals with a shielding, with a hood around it, they shine down the track quite a ways. Now, you may still see this a little bit when you're crossing the tracks. If you look down, you may line up, just because of elevation and so forth, with the train signals in the distance. And you may notice that they get quite bright for a brief instant, and then they go back to their normal dullish color. And this would be an example of a Fresnel lens working there as well. This is a diagram taken from the internet, just to show you how this used to work. So you'd have your light source here, an arc lamp or whatever. You have your Fresnel lens from here to here that's focusing the beam. And then you had reflectors, kind of like Venetian blinds here and here, reflecting the light outward. So we took, instead of just a small pencil of light that you would have had in the old days, now you took almost half the radiated light and sent it out in a beam. So naturally it's going to go maybe 20, 30 kilometers out to sea if the conditions are even appropriate. This is going to allow boats much farther away than normal, but pretty much at the limit of just the curvature of the earth, to be able to see these lights at shore. And again, like I said, certainly saved a lot of lives in the sense of people, captains and the navigators, knowing where they were, especially under quasi-foggy conditions or sea haze or just whatever.
So here's a
lighthouse that has a Fresnel lens in it. You can see that there's a band of glass that goes all the way around. There are 4 Fresnel lenses, and then there's at the top and bottom you'll see the louvered shutters to reflect the light, as I showed in the previous diagram. And so what happens is that as the light shines through the Fresnel lens, it's focused in a beam. Because the lens is rotating, you get this beam sweeping around the region, and if you're on a boat at a distance, what you're going to simply see is a blinking light as the beam passes over you. So this is a way to take a light that is of given brightness and make it shine much farther away than you would otherwise be able to. We also see here in this case, a green light from a railway signal that shows the same Fresnel pattern to it that allows these lights to be seen at a much greater distance, and this is really necessary given the enormous stopping distance issues that railroads tend to have. So the end of this little part of the story comes with perhaps a less than ideal situation, and that is that, okay, we've got this light, is clearly got wave character. The only way that they understand waves in those days is mechanical waves, where there's a medium of something vibrating, air, a drum head, strings, whatever. And now you have a situation where light is coming from the universe and it is traveling through a vacuum. And we know it's a vacuum because the Earth and the planets don't slow down. And so as a consequence, what allows the light to vibrate its way through space? And they had no answer for this. So they invented something. They said, well, there must be this mysterious material that's massless, that doesn't provide any drag, that all it does is allow light to propagate in the way that we observe it. This was known as the luminiferous ether. And Fresnel was a big fan of it, as well as the others. And but I think a lot of people in mainstream science were never really quite happy with it, and we'll see more of that story as we go on. So here we are in 1825, 1826 or whatever. We have pretty much agreed that light has a wave, that the corpuscular ideas of Newton have been more or less discredited, and we've invented, or at least perpetuated, the invention of this mysterious material called the ether, which allows the transmission of light through vacuums. Now, no one knew what to do with all this, and not everybody was happy with it. But it ended up by through the 30s, 40s, and 50s, not much progress was really made until we got into the second half, if you will, of the 1800s. And that, of course, will be the next lesson. Thank you so much for watching, and hopefully you found this video helpful. If you're enjoying this, please consider subscribing and giving the video a like. Thanks for your time.